Our last example for Chapter 6 is an interesting problem. It's got, a lot going on. In this example, we're asked to consider two masses, M1 and M2, attached with cables. So we're going to be swinging in a circle. So the center of the circle is here. M1 is going to be spinning in a circle of radius R1. M2 will be spinning in a circle of radius R2. And we're told that these cables are swinging at constant speed. So it's a vertical circle, so gravity, as we can see, we're going to put into the problem in a moment. Gravity is in the problem. And even though it would be difficult with gravity, slowing the mass down as it goes up and swinging it around, but let's just take it for granted that we're capable of doing it. So it's spinning at a constant speed. And we're going to assume that the masses remain lined up as well. So the cables are tight enough, taut enough, that M1 and M2 are going to swing around together, so that when M2 makes one complete circle, M1 also makes one complete circle. All right, and we're asked to come up with equations that would let us calculate the tension in each cable when the masses swing to this bottom position, and then we're asked what equipment would we need to actually make those measurements, and how would we carry that out in a laboratory environment in the classroom. So let's first take a look at what we need to do with our circular motion analysis. And I have down here what I hope at this point is well understood by everyone, that we have sum of the forces in the radial direction equals mv squared over r. And radially in is going to be our positive direction, so we're going to take any radially in forces and make those positive. Any radially out forces we make negative. Mass, of course, is always positive, and I have in here that we have no circular motion without, and I left out some words here, without a force net radially in. So some of the forces in the radial direction gives us our force net, and it has to be a net radial force inward to have circular motion at all. And we are being asked to focus our analysis at the bottom. So we're first going to look at M1 and then look at M2. So M1 I'm going to highlight in green here. And when we look at M1, let's look at our force diagram. Well, gravity is in this problem. So we have M2G pulling straight down. In brown, I have my cable attaching mass 1 and mass 2 labeled as cable B. So tensions pull, never push. So we have tension B pulling up on M2. And those are the only two forces acting on M2. And let's go up to M1 and see about our forces acting on M1. So on M1, we have M1G down, so we have gravity pulling straight down. Cable B, tension B, is also going to be pulling on M1. Tensions pull, never push. And then finally, we have the cable attached at the center of the circle, attached onto M1, and cables pull, never push, pulling up on M1. So for M1, the inner mass, we have that the sum of the forces in the radial direction equals tension A radially inward, that's positive, M1G outward, so that's negative, tension B also pulling outward on mass 1, so there's the sum of the forces in the radial direction, equals mv squared on r. And notice I have to put an index on m, v, and r. They will be different for mass 2, right? Obviously, mass 2 will have its own mass. Mass 2 will also have a different speed, right? Because mass 2 is completing its circular motion in the same amount of time it takes mass 1 to complete its circular motion. However, mass 1 is on the inner radius, so it has a much smaller distance to travel. So mass 2 is actually going to be moving much faster than mass 1. So I can't just label them with the same V's. So M1 has its own speed, V1, and obviously the radius is different, so we have R1. So I'm just going to box that as I have here and leave that and go on to M2. So M2 I'll do in blue here. And let's look at the M2 forces. M2 has some of the forces in the radial direction. Tension B now, radially inward, and only gravity radially outward equals M2 V2 on R2. And again, we have to have a separate index for the M2 variables. Well, we now have our equations that we will use to solve whatever we have to solve for regarding mass 1 and mass 2. But the trick to really seeing what's going on here is to notice that the frequency of revolution, the number of revolutions per second, is going to be the same. So the same revolutions per second for M1 and M2. So I don't need a separate index for frequency or for time. So this is going to be the key to solving this problem. Speed equals distance over time, and the distance is not going to be the same for M1 and M2. Remember, the distance for M1, the inner mass, which I was doing in green, M1 is going to have that shorter distance, 2 pi r, but the period of motion I don't need an index on. That's the same. And I can leave my equation either as period of motion or frequency of motion. So 2 pi r1 over t, or 2 pi r1 f. And then for v2, we have 2 pi r2, and I was using green, blue for M2. So 2 pi r2 is equal to the distance d2. And so there you go, r2 d2. How about that? Anyway, the distance d2 is 2 pi r2 times f, and we don't need the subscript on the frequencies because the number of revolutions are the same. So now I have these 4 boxed equations. So I have 1, 2, 3, 4 at my disposal. And let's take a look at what it would take to numerically solve this if this were actually occurring in the classroom. So if we were spinning these two masses in the classroom and we wanted to think about what equipment would we use to actually do this experiment, well, we would need a meter stick or a ruler to measure R1 and R2. So meter stick or ruler is what we would need for R1 or R2. How would we measure the time, however, if it were spinning really quickly? Because you'd have to spin this thing pretty fast to keep everything in unison and the cables tight enough for M1 and M2 to spin together. So we need to somehow get the revolutions per second, right? Or the amount of time it takes to go around in the circle. And here is a trick that you should think about when you're possibly looking at AP test questions, where they'll ask you what equipment you might want to use to solve these types of problems. How about a stopwatch, right? Well, the problem with the stopwatch will be that if they're telling you it's spinning really fast, your human reaction time and your ability to start and stop the stopwatch would not allow you to calculate the amount of time it takes to go around once. However, the trick we will use in the lab, if we do this circular motion experiment, and we'll do one like it, will be to measure multiple revolutions, right? So we're going to let it spin 10 or 20 times. That allows us to have the human reaction time And to reduce our error by just counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, stop. And that amount of time, that longer amount of time, is something we can do with a stopwatch, and then we divide by the 20 cycles or 20 revolutions that we just counted to get the revolutions per second. Once we have the revolutions per second and we have our meter stick measurements for R1 and R2, we now know V1 and V2, right? We just said we meter stick measured R1 and R2. We could either digital balance or triple beam balance, measure the mass M1 and M2. We would calculate M1G and M2G are therefore known. And now we would have two equations and two unknowns to be able to solve this problem. So you can see how a system that when we started maybe looked very complicated and difficult to solve, when you're able to break it down into individual forces, establish a good analysis and equations that govern the motion of the particle, you're then able to carry that information into a laboratory experiment and actually make concrete measurements. Well, I hope you enjoyed looking at this problem and Chapter 6, and we are then going to be on to energy and looking at a couple chapters of introducing energy considerations and a new way of looking at our physics problems coming up.